Alright, so this is the last video that we're going to focus on for this part of our unit. We're going to be talking about bond properties and energies. Just some general characteristics of bonds. Sometimes you will talk about bonds in terms of their order, and that's just representing how many electron pairs are being represented in that bond. When you have an order of 1, you're representing a single bond, a 2, a double, and a 3, a triple. If you're dealing with a resonance structure where a double bond is alternating, then they might be getting an order of 1.5 since the double bond is split between them. Or if you have a double bond that's splitting between 3 different individual bonds, then they might each get an order of like 1.33 since each bond would basically getting 1 1/3. The length of a bond is going to depend on the number of electron pairs that are present in that bond. Um, the more electron pairs that are present, the shorter the bond gets. So your single bond is the longest, and therefore it's the easiest to break. Double bonds are a little bit shorter, and then triple bonds are the hardest to break. They are the shortest of the bunch. Um, and then we're going to talk about strength. We're going to talk about the energies associated with breaking bonds and forming bonds. We're going to be dealing specifically with gas products and reactants. In order to break a bond, you have to use energy. It's an endothermic change. And that's what's going to happen when your reactants break apart to form your products. When you form those products, you are going to release energy in the process of forming bonds, and so that's going to be exothermic. Um, as I just talked about, your triple bond is always stronger than your double bond, and then the single bond is the easiest to break. So we've done enthalpies of formation before, where we took the enthalpies of the products and we subtracted them from the enthalpies of the reactants. And the enthalpies of formation basically told us how much energy was needed to form that substance, or how much energy was needed, was released to form that substance. This here is just dealing with individual bonds, and when you combine the individual bond energies together, you can determine the enthalpy of formation for your substance. And so I would not expect you to know this chart. If you'll notice, you have enthalpy values for a variety of nonmetals listed here, and then those are for single bonds up at top, and then at the bottom you have them for double and triple bonds. And so a table like this would be provided for you if you were asked to do a problem like this on an assessment. So you just need to know how to use it. What's going to make this a little bit different than the enthalpies of formation is that we kind of switch the order in which we do the subtraction. Because all of the bond energy values that you just saw were positive, what we do is take the energy that was used to break apart the bonds and we subtract away from it the same values, but the energy that was released in the process of making the new bonds. And by doing that, we make the exothermic component when the energy is released possible, and we also keep the endothermic component, the energy that was absorbed to break the bonds together. So rather than products minus reactants, where the compounds and elements are all taken care of as they are, because we're dealing with individual bonds, we switch it and take the bonds that are broken and subtract from them the bonds that are formed, or the energies for the bonds that are formed. So I've got here for you, we're going to take methanol and carbon monoxide, and we're going to make ethanoic acid. We have the structures there so that you can see what types of connections are present in these molecules. So in methanol, you have 3 carbons, hydrogen bonds, and you have a carbon-oxygen bond, and you also have an OH bond, similar to what you see over here in the ethanoic acid. So those are the types of bonds that we have present in methanol. I usually like to list the types of bonds because if I see something that is both being broken and then being formed, the energy change is a wash, and I can kind of cancel those out. We also have the carbon triple bonded to oxygen and carbon monoxide. And notice I'm putting the numbers that we had 3 of the CHs, 1 of the COs, and 1 of the OHs in methanol. If there had been a coefficient in front of any of these substances in the balanced equation, then you would have had to multiply the number of bonds by that coefficient. So you do still have to account for the stoichiometry of your reaction. On the product side, we have again the 3 carbon hydrogen bonds, but we also now have a CO bond between the carbon and oxygen at the end of the molecule. We have a CC bond between the two carbons, the OH bond at the end of the molecule, and we have a C double bonded O. So those are all of our connections. Again, the ones on the left are going to use energy, the ones on the right are going to release energy. Because we have some common connections in terms of the carbons and hydrogens, and in terms of the carbon-oxygen, and in terms of the OH, those bonds we can put in our calculation, but we really don't have to. We really just need to focus on what changes. So if we go back to our chart from the previous slide, we can see that the energy for C triple bonded to an oxygen would be 1046 kilojoules per mole. We only had one of them, so it would be 1 times that. And then we're going to subtract away the energy for a carbon-carbon bond and a carbon double bonded to an oxygen. And so I believe the carbon-carbon bond is the 346 kilojoules per mole, and the carbon double bonded oxygen was 745 kilojoules per mole. Again, the ones are coming from the fact that there was one of each of these. Once I simplified the different types of bonds that were present in these molecules, if there had been a coefficient, they would have been multiplied by that coefficient. So the moles cancel out, and I would take 1046 and subtract from it 346 and 745. And what I find out in that process is that negative 45 kilojoules of energy would be released, 45 kilojoules of energy would be released, or there are a change of negative 45 kilojoules for this reaction to proceed. This is actually representing HC2CO2. This is representing the formation of vinegar or acetic acid. And so to form acetic acid from methanol and carbon monoxide, you would release energy. If you had determined the enthalpy value for this reaction using the enthalpies of formations that I'd given you previously, you would get a value pretty close to this as well. So whether you do it using bond dissociation energies or whether you do this type of problem using enthalpies of formation, the enthalpy of the reaction isn't going to change. But what you do need to make sure you keep straight is that you have to take the energy from the bonds broken, determine the amount of that, and then take away from that the energy that's released with the bonds being formed. Because they're always positive, you need to make sure the bonds being formed are subtracted away from the bonds being broken. And that should get you through the rest of the unit.